Welcome to this next video in the playlist on group theory. In this video what we're going to study is the concept of a group homomorphism. Okay, right, so let me just outline how we're going to actually approach the question of what a group homomorphism is. So we're going to start off by having a little bit of a refresher on the concept of a group isomorphism. Okay, and then what we're going to see is that a group homomorphism is really just a generalization of the concept of a group isomorphism. Okay, right. Now before we actually begin that, let me just give you a little warning about the spirit with which we are approaching this in this video. Okay, so the concept of a group homomorphism is much more complicated and much more difficult to understand than the concept of a group isomorphism. Okay, and you're probably not going to get the complete big picture of what a group homomorphism is until much later videos where we look at quotient groups. Okay, when we study quotient groups and the first isomorphism theorem, then you will have a complete big picture of what a group homomorphism actually is. In this video we are not going to get to that, okay, and you may never get a complete big picture of what a group homomorphism is in this video. Okay, instead what we're going to do is we're going to take on little nuggets of understanding about group homomorphisms. Okay, so we're going to develop lots of little theories which are going to help us eventually build up to the big picture of what a group homomorphism is. We're going to need all of these little nuggets of understanding in order to build the big picture of what a group homomorphism is and discuss quotient groups in later videos. Okay, but it may seem quite unmotivated bits of this. Okay, so we're going to discuss lots of little nuggets of theory, and you might be sitting there thinking, I don't care. I want the big picture of what these actually are. I don't want little tiny trivial things like this. Okay, well, the way you need to approach this is that you need to think that these little nuggets that we are biting off, basically, that they are going to help us get to the full picture of what a group homomorphism is. So that's the way that you should approach this. We're going to have lots of little nuggets of understanding about group homomorphisms, but in this video do not feel guilty if you do not ever get the bigger picture of what a group homomorphism is. We will do that in later videos, and we'll use all of these little nuggets of understanding that we're going to develop in this video to build that bigger picture of what a group homomorphism is in later videos. Okay, so that's my speech about how you should approach what we're going to do in this video. Right, so let's begin by reminding ourselves of the concept of a group isomorphism. Okay, so remember, a group isomorphism is a mapping which we have in previous videos called phi. Okay, so this is our group isomorphism here, and it's a mapping between two groups. So we'll call the domain group capital G, and we'll call the codomain group capital G prime. Okay, so here is our isomorphism, which is mapping the elements of our group G onto the elements of our group G prime. Okay, now if this is going to be an isomorphism, and I'll just write out the word isomorphism, I probably should at least once in this video. Okay, so if this is a group isomorphism, then this needs to be a bijective map from G to G prime. Okay, and that's really what we're going to change in order to generalize this to the concept of group homomorphisms, but we'll talk about that later on. Okay, right, so back to group isomorphisms. Phi is a bijective map from the group G, and I'll just draw out the group G here. So remember, the group G is fundamentally a set of symbols with a composition law on it. So here is G, and I'll color code it up in red here. Okay, and we are now going to have this mapping phi, which is going to take every symbol in G and map it onto a symbol in G prime, basically. Okay, so here is the set for G prime over here, and we'll color code G prime in green over here. Okay, now, if phi is a bijective mapping, which it needs to be if it's an isomorphism, then what that means is that it is both surjective and injective. Now, surjective means that every element of G prime gets some element of G being mapped onto it. Okay, so the mapping is onto, basically. Injective means that every element of capital G prime gets only one element from capital G being mapped onto it. Okay, so it's a one-to-one mapping. Okay, so what this really means is that we are taking the symbols of G and relabeling them with symbols from G prime, basically. We are turning the symbols of G into symbols in G prime, and every symbol in G prime has a symbol in G that's being mapped onto it, and only one symbol in G is being mapped onto it. Okay, that's what we mean by bijective. So that's the way you should think of this isomorphism phi, as a relabeling map that is relabeling up the elements in G with elements in G prime. You can imagine it changing the symbols of G into the symbols of G prime, basically. Okay, so it's a bijective map, but it has to be more than that. Okay, it can't just be a relabeling map. The relabeling map has to have an incredible property, basically, and this relates to the composition laws on these two groups. So let me now just draw out the composition tables for these two groups. So here we'll have the composition table for red here. Okay, and we'll have the composition table for green over here, and I'll just color code these in. So here is our composition table for the red group, and here is our composition table for the green group. Okay, now, what we know is that this isomorphism is relabeling up the elements of G with the elements in G prime. Okay, so what does that mean for the composition table? Okay, well, remember the composition table will have every element of this group given a column, so all the elements of the group will be listed up here, okay, and every element of the group will also be given a row. Now what we can do is we can relabel up all of those labels for columns and rows, all of the elements of the group that are up here and down here, we can relabel them up with what they are in G prime, and that will turn our titles for the columns and our titles for the rows here into the titles for the columns and titles for the rows in G prime, basically. Okay, so we can relabel up, if I just get another color, we can relabel up these portions of the composition table, okay, with these portions of the composition table of green over here. Okay, so any relabeling map can do that. The big thing that we want isomorphisms to be able to do is they will also relabel up all the entries here, all of the actual entries in the composition table. Okay, so all of the answers to what one thing composed with another thing is equal to, and they will turn this into this perfectly. Okay, so we know that any relabeling map can successfully relabel up this portion and this portion into this portion and this portion, but we don't know that it will actually turn all the entries of the composition table into the correct entries over here, and that is the big property that an isomorphism is going to have. It is actually going to turn this composition table into this composition table when you apply it. So if I take this composition table on the red group here and use my relabeling map here, I go through and relabel up all of the elements of G that are in this composition table at any point with what they are now equal to under this relabeling map. Okay, so elements in G prime. It has to actually turn this composition table into the composition table of green. That is the incredible property of isomorphisms. Okay, and if there is an isomorphism between two groups, capital G and capital G prime, we say that the two groups are isomorphic to one another, and what it really means is that the actual algebraic structure of these two groups is the same. You've just used different symbols to express it, but it's the same fundamental algebraic structure. Any theorems that hold for this one will hold for this one, because all that's different is the symbols you have chosen to use, which are meaningless. Okay, if you had been an alien, you could have come up with different symbols, but the algebraic structure is the same, basically. Okay, so that's the concept of two groups being isomorphic, and it's a very, very powerful concept. Okay, now, there is a way of expressing this concept that when you relabel up one composition table, the composition table of the domain group, you get the composition table of the codomain group. There is a nice succinct way of expressing that, okay, which I just want to go over now. Okay, so let's think of two arbitrary elements of the domain group, capital G. So let's think of little a and little b, which are arbitrary elements of the domain group here. Okay, and let's think about what those two things composed together in the red group, the domain group, are. Okay, so let's say we've got little a here, and we've got little b here in our red group composition table, and of course the answer is little a composed with little b. Okay, so that's nothing difficult. Okay, so we've just got two arbitrary elements of our domain group here composing together to give an answer in the red group. Now, let's think about what this isomorphism phi will map little a and little b onto. Okay, so phi will turn little a into phi of a, which will be an element in G prime. Phi will also turn little b into phi of little b, which will be an element of G prime. Okay, so we've now mapped a and b onto what they are relabeled as under this relabeling map phi. Okay, now what I can ask is, what is phi of a composed with phi of b? Well, that will be set in my composition table on green. So here, this is now my composition table on green. Okay, and there is some answer to that in the green composition table, which is phi of a composed with phi of b. Okay, so this is the answer that is set in my codomain group, which is my green group, its composition table basically. Okay, so what I now know is that this mapping, phi, it will relabel a and b up as phi of a and phi of b. Now, if we really want this composition table to be turned into this composition table under this relabeling, we better damn hope that when we relabel up this entry here, A composed with B, that it equals this entry here, because we know that phi of A and phi of B have no choice. They're being mapped onto this. In fact, I might even draw this, that A is being mapped onto that, B is being mapped onto that. We want A composed with B to be mapped onto that. Okay? And that's not trivial at all, because phi of A composed with B is phi of A composed with B. It's not necessarily equal to phi of A composed with phi of B, where this is the composition in the composition table green, and this is the composition in composition table red, basically. Okay, so this is how we can succinctly express the fact that these two composition tables have to be the same. That when we relabel up the entries in this composition table, it has to turn it into the entries of that composition table. Okay, so this is the great criterion here. Okay, and that has to be true for all little a and little b is an element of capital G. So for all little a and little b you can pick, i.e. for absolutely every single entry in this composition table, it has to be true that this is the case. And that then is this condition that when we relabel up the entries of this composition table, we get this composition table. These two are truly the same composition table, but for the fact that you've used different symbols to express it, basically. Okay, so that's this criterion that isomorphisms have to then obey. Phi of A composed with B is equal to phi of A composed with phi of B. Okay, right, so there is what an isomorphism is. Now what we're going to do then is use this to generalize, well, we're going to generalize this and arrive at the concept of a group homomorphism. So a group homomorphism is a very similar concept, okay? Again, we'll denote it phi, and it's a mapping between two groups. So a homomorphism is a mapping from one group, which we'll call the domain group, to another group, which we'll call the codomain group, okay? So now this is going to be our homomorphism this time, rather than isomorphism. And this time, the big difference is that this time, this mapping doesn't actually need to be bijective. Okay, it doesn't need to be bijective. That's the huge difference. In the case of an isomorphism, this had to be a relabeling map, which exactly relabeled up the elements in G with the elements in G prime, turning G into G prime. Okay, this time it doesn't have to be bijective. However, you still do have to have this criterion satisfied. So we still want the criterion that phi of A composed with B is equal to phi of A composed with phi of B for all little a and b is an element of G. Okay, so we do insist on that criterion. Okay, that it doesn't matter which order you do the composition in. Either you can compose A and B together in the domain group and then take what the answer is mapped onto, or you can firstly map A and B into the codomain group, okay, and then compose them together in the codomain group, and the answer will be exactly the same, basically, is the idea. Okay, it does not matter which order you do those things in, whether you compose first and then do the mapping, or do the mapping first and then compose, basically. Okay, right, but this is no longer necessarily bijective. Now note, it's not the case that this isn't bijective. There's no rule saying this can't be bijective. It just doesn't have to be bijective. So in fact, a homomorphism is a generalization of the concept of an isomorphism. All isomorphisms are homomorphisms, okay? But not all homomorphisms are isomorphisms. The homomorphisms which are not bijective are not going to be isomorphisms, whereas the homomorphisms which are bijective, those will be the isomorphisms. Okay, so this is the concept of a group homomorphism. Okay, now we're not really interested in the group homomorphisms that are bijective, because of course we've already studied those. Those are called isomorphisms. Okay, what we are interested in is the ones that are not actually bijective. Okay, so what I just want to do now is spell out the two reasons for which a group homomorphism can fail to be bijective, basically. Okay, so it helps when we're discussing this to draw pictures. Okay, so we'll have our domain group represented here by this circle. Okay, so this is representing the set of the domain group. Okay, and once again I think I'll color code this, so we'll stick to our color coding and we'll have the domain group here in red. Okay, and then we'll have the codomain group here in green. Okay, and once again this oval shape here represents the actual set. Okay, right, so in order to be bijective, remember there are those two criteria that you have to obey. Okay, number one, you have to be surjective. Okay, and surjective means that the mapping is onto. Basically it means that if you take any element in G prime, so any arbitrary, let's say little g prime here, in capital G prime, that there is some element which we'll call little g in G that is mapped onto little g prime by the mapping. So basically, surjective means that for all little g prime is an element of capital G prime, there needs to exist a little g which is an element of capital G, such that little g is mapped onto little g prime by our mapping, such that phi of little g is equal to little g prime. Okay, so one of the reasons that our mapping phi can fail to be bijective is that it fails to be surjective, which would mean that there were some elements in capital G prime, maybe this little portion at the bottom here, okay, which I'll colour in a different colour. So this little portion that I'm colouring in orange, let's say that the elements in that orange section, they do not have any elements in capital G being mapped onto them. Okay, so there are some poor little elements in here that don't get any element in capital G being mapped onto them. Okay, that would be one reason why this mapping phi failed to be bijective, that there were some elements in capital G prime which simply did not have an element in capital G being mapped onto them. Okay, so the mapping was not onto, it was not surjective. Okay, so that's one of the things that this mapping could fail to satisfy in order to mean that it wasn't a bijective homomorphism and therefore it was a non-bijective homomorphism. So it wasn't an isomorphism. Okay, right. The other thing, and the more interesting thing we'll find out, because later on we're going to find out that actually we don't need to bother studying the homomorphisms which only fail to be bijective because they're non-surjective. Okay, we'll see how any non-surjective homomorphism can be reduced into thinking of a surjective homomorphism. That's one of the things we'll do in this video. Okay, right. The more interesting reason that a homomorphism can fail to be bijective is that it fails injectivity. It fails to be injective. Okay, so what is meant then now by injective? Okay, well, injective, the sort of tongue-in-cheek way of saying injective is that the mapping is one-to-one, basically. Okay, this means that if you take any element in G' that actually has elements in G being mapped onto it, that it only has one element of G being mapped onto it. Okay, so it means that for all little G' is an element of, and I'm going to use a bit of notation that we haven't previously used, the image of the homomorphism. Okay, phi. So im here means image. Okay, and phi is obviously our name for the homomorphism. Okay, so for all little G' is in the image of the homomorphism, and what this means is all elements of the group, the codomain group big G' here, which actually have an element of big G being mapped onto them. So basically this is the subset of big G' that actually has elements in big G being mapped onto it. So I've got rid of all of the elements that don't have any element in G being mapped onto them at all. I've got rid of this orange portion, if you like, here. So for all little G' is an element of the image of the homomorphism, the portion of G' that actually has an element in G being mapped onto it. So if I give you the formal definition of what the image of a homomorphism is, okay, it's equal to everything that's of the form phi of little g, where little g is an element of capital G. So basically what you'll do is you'll go through every element of capital G here, you'll take what it's being mapped onto in G', and you'll stick all of those elements into a set. That's what is meant by the image of a homomorphism. All of the elements of G' that actually have an element in capital G that is being mapped onto them, basically. Okay, right, so I'm saying that for all little G' which is an element of the image of the homomorphism, i.e. is an element in capital G', which has an element in G being mapped onto it, there exists one and only one. There exists only one G is an element of capital G. Little g is an element of capital G, such that phi of G is equal to G'. Okay, so basically injective says that you don't have multiple elements in capital G being mapped onto the same element in capital G'. So basically if it was not injective, it would mean that there were two or more elements in capital G being mapped onto the same element in G', basically. Okay, so for instance, let's take this little G'. If both G and G' here were being mapped onto little G' by this mapping phi, then we would say that the mapping was not injective. It was not one-to-one. Instead, it was many-to-one, basically. Okay, right. So that's another reason that a mapping phi can fail to be bijective, basically. It can fail to be injective. And of course, homomorphisms can fail to be bijective because they fail both of these criteria. They can fail to be surjective and injective. Okay, now we'll call it there for this video, and in the next video what we will do is we will develop an understanding of why we can throw away the having to think about non-surjective homomorphisms. We can always reduce a non-surjective homomorphism into thinking about a surjective homomorphism. And then the only important reason then that a homomorphism can fail to be bijective is that it's not injective, basically. You have more than one element being mapped onto the same element in G'. Okay, so we'll do that in the next video.